this is a sat encoding to compute a periodic tiny rhythmic canons. This is a joint work with many authors. Here's Stefano, Gualandi, Gennaro, Auricchio, Greta, Lanzarotto, and Pernazza. So the talk is this is the outline of the talk. First we see that what is a rhythmic canon problem, and we can see from two different perspectives, from a set model perspective and from the other perspective, and we will see how can this outline can be seen as a polynomial representation, and that we can compare to other methods in this area that are the search methods for the fill out procedure and the cutting sequential algorithm in this setting. And then we can set up in this talk our SAT model for this tiny rhythmic canon problem, and we will see finally in this setting. So about this problem, a tiny rhythmic canon can be characterized by a single same motive that can be translated in time, as we setting here, and with two main voices: the A voice that we will call the first voice A, and the other voice that is called the B voice. So the A voice plus the B voice cover all the tiny rhythmic canons. In this example here, we have the A voice have many different beats here in the 1 second and in the 7th position. So we have this shift of the A voice here. So for the first, the second, and the third one. Okay, in a mathematical way, tiny rhythmic canons can be represented by a couple of subsets of Zn, where Zn is the cyclic group modulo 0 from n-1. So we can define this application that will be called sigma, that sends each couple of elements that lie in the direct product of A and B to the remainder classes of the cyclic group Zn in such a way that we can see that if sigma is bijective, we can cover all the cyclic group Zn. So we can see that say that A and B are in direct sum if the sigma function is bijective. So a tiny rhythmic canon in a mathematical way, we can see that a tiny rhythmic canon of period n can be decomposed into different subsets A and B, such that all the integers from 0 to n-1 can be covered in this way. And it is very important to point out this remark here, that if A is a tiny complement with a certain voice, be any translation of A plus Z with Z as an integer in this set, it is still a tiny complement of B. So so A plus B, it is invariant under translation in this setting. This is very important. So in a graphical way, we can see that A is the inner voice of the canon of this canon, and the B is the outer voice given by the set. So the A voice is given by the set 0, 1, and 5. So in this graphical setting, we have this sort of sequence of cell where the fill boxes here are the black cells that is given by 0, 1, and 5, and the set B is the shift of the A set. So our main goal is that in each column we have just one exactly black box. If you sum each number of the A set with each number of the B outer voice, we can cover all the integers from 0 to 8 modulo 9. Yeah, this is the main problem why we are studying the aperiodicity of a tiny rhythmic canon. So a rhythm A that is a subtype of a cyclic group Zn is periodic modulo Z if and only if we can shift that set A with a certain element Z, we can still in the set A. So, but we are really interested in finding aperiodic tiny rhythmic canons. Here, we can see that in Z16, we can decompose the voices in the upper part with 0 and 6 and 0 and 8. Example here. So, what is an aperiodic tiny rhythmic canon can be seen as a Vusa canon, where a Vusa canon is a tiny rhythmic canon where if both A and B are aperiodic tiny rhythmic canons. So in this example here in the previous slide with 0, 1, and 5, the A voice is given by the set 0, 1, and 5. And we can see that in the previous slide in a graphical way, we can shift the A set with 3. So we can cover the first row, the second row, and the third row. So the periodicity of this set is 3 with respect to that rhythm. Instead, in the B voice is not periodic without any Z in any period. So the aperiodicity constraint can be decomposed and can be written in the following form, taking into account of this important remark that a set A is periodic modulo Z if and only if we can check that is modulo all the non-trivial multiples of Z dividing n. So it is enough to show that the set A is periodic modulo all maximal divisors of n, where a maximal divisor is the largest number that is written in the following form. It is the quotient of n, where n can be decomposed in the following form. It is a product of the prime number of n. So we denote as Dn, capital Dn, and quotient P, with the P is a prime factor of n. This is it turns out to be useful, this kind of representation of a canon, since this can be translated into a linear constraints. So if we have A that is a rhythm in Zn, and we can set up the characteristic polynomial of A in that form, we can see that if we multiply the characteristic polynomial of A and we multiply with the characteristic polynomial of B, we can obtain all the complete polynomial modulo x n minus 1 in Zn, where all the coefficient of the characteristic polynomial of A and B lies in 0 and 1. So the main problem with this characterization is that the aperiodic tiny complements problem consists in finding all the possible aperiodic complement in B. So this problem has not a single solution, but many solutions, such that we can cover all the cyclic group Zn. Here we can see a simple calculation with the polynomial representation of the motive A and of the motive B. So the characteristic polynomial of A is given by that polynomial x5 plus x plus 1, and the other one, since B is a complement of A, is given by 0, 3, and 6. And so if we multiply the first polynomial with the second one, we can obtain the all complete polynomial modulo and x9 minus 1. taking into account that in modulo x power 11 can be decomposed in that simple way. So these are methods that are well known in literature. The first one, it is the fill out procedure, that is an enumerative algorithm that sets the set P0, and we can add one by one a possible complement of A, and this one that is called, the other one that is called the cutting sequential algorithm, it is an integer linear programming model using the polynomial representation that I have mentioned before. It uses 0, 1 variable, and can be used within a cutting plane framework in such a way that we can add one by one and no good constraints, since when we find a new possible complement, we cannot retrieve the same solution many times. So we can use this kind of complement B as a new linear constraint. And the main difference between the cutting plane framework in the cutting sequential and the first one is that this one can be not used with a post-processing. Because we can add in this framework here the translation constraint, since, as I mentioned before, a possible translation can be a solution to this problem. And so we have set up a sort of a linear constraint to not retrieve this kind of complements in that framework. So this is the main ILP model that we can use. So given a period n and the characteristic rhythm A that is given in that vector here, we can construct the circulant matrix that the columns of this matrix are the circular shift of the characteristic vector A in such a way that the tiling condition is fulfilled. The tiling condition can be written as a partitioning condition in such a way that we can think of a canon as a sequence of cells. So we can select the column in such a way that we can cover all the integers from 0 to 1. So we introduce a literal xi that represent the binary variables indicating the bits of the rhythm B. So the tiling condition can be formulated in this following form for each column and for each row. For the aperiodicity constraints, in the same way from the graphical point of view, we have a sequence of cell, and we can group this cell into n quotient D groups in such a way that if we fill a cell in a certain group, that type of cell black or white cannot be the same in the other groups. So the indicator variable y di for each maximal divisor D in the set dA stands for that all the variable must not of the same type. So this sum in the third sum, we can say that all the variables must not be active, and so we can translate the two and the third constraint in a linear way, where the y variable for every maximal divisor D and every position I can be stated as the true variable, so the black box, and the ZDI for the white box. And we can see that the sum of the y and the z can be 1 exactly. So between z and y for every I from 0 to d minus 1, and for every maximal divisor in the capital Dn. The tiling condition can be translated in a SAT formulation with exactly one constraint, that is the conjunction between the at least one and at most one in this simple form. So we can take all the possible combination modulo n and this junction that goes through the set A. And for the aperiodicity constraint in the following form, we make use of the logical equivalence between the closed C1 that is given by the indicator variable y that I have written before here, and then for that part that all the cell must be black or white, so the bit is present in that cell or not, and this one can be formulated in this formula, and then we can combine the first part with the second part, joining 7 and 8 in a conjunctive normal formula, and this is the main model that we are using for the aperiodic tiling rhythmic canons. So in this slide we have so our code, it is written in Python using the ILP model that I have written before in Python, and then the SAT encoding model, and this experiment are run in this computer, and the code can be downloaded in this link, and then we can move to the description of the test. So the main reason of this test are two goals. So the first one, we can compare the time of our model to the SAT encoding model, and we have shown that in our case we can set up, and we have to find tiling complements where n is huge. It is a huge number, and for the test phases we have considered the rhythm 72, 108, 120, and this one are just the tiling aperiodic canons. And with the SAT formulation, we have completed some new complements canon, where the n is greater than 168. So here we have the main table comparing the run times of the previous method that are well known, the fill out procedure and the cut sequential algorithm for different parameters, because we can set up different parameters that depends on maximal divisor. Here we can see that the SAT encoding model is much better than the other one. And then for the final part, we have shown that in this column, in the last column on the right side, we have found all the possible complement in a reasonable amount of time with the SAT encoding model, with that specific parameter, 5 parameter, with P1 and 1, P2 and 2 and then 3 for every maximal divisor that are listed in the left side. Thank you very much for your attention.
To repeat the question before answering them, or
for the okay for the
how do you divide the time? Because the reason, like how do you divide, like there's a binary time,
binary time. So how can okay, so the time can be divided. So how can we divide the time in the motive A or B? You mean, because we have two different times. So okay, So I think that I refer to the first slide, or maybe the
Yes, here that's the same, but take a real partition sheet.
here.
The next one,
Okay.
you know, that's not the same time this one as this one.
Okay. How can we partition? So we take just into account of each single bit, not of the rhythm itself. So we can, because here we take into account of each voice, also the melody itself. So that's why it's the main difference between the voice and the rhythm itself. I don't know if I am clear about the question. It's not. It's clear what I mean.
For instance, in your example, is this one bigger than this one? The square, the black square?
Oh, no. Okay. No. So the base metric is the semicron here. The semicron in English, so the main bit is this. So is this one.
Okay.
That's
so
why it's based on each bit. Yeah.
And when I switch from binary to ternary, then it's not the same division.
It depends. In this case, we have set up that each single cell is the same kind of bit.
I guess could you easily adapt it to be like smaller intervals? Or
Can you repeat faster?
Can we set up this kind of setting for smaller interval? You mean?
Yeah.
Okay,
like,
for smaller.
Pretty easy to modify your code to do that.
For smaller interval, I think for our purpose, it is easy to set up for smaller interval, but for larger, I think is more interesting. I think for larger interval than that smaller interval. Yeah, I think so. Thank you.